Okay, we are here on the upper part of Cherry Creek in Marquette County. We're going to demonstrate the status and trends random site protocol habitat survey. It's the standard survey done throughout the state. There are data sheets that are used for the survey. You should already have them, but if you don't, those should be. You can contact us. You can send me an email, I guess, to get them. zornt@michigan.gov. Or you can get them from the biologist in your local area. One of the first data sheet has some information about the site, water body name, the station, the date. Here's the equipment that you need for measuring habitat. It's listed on the sheet itself. It's just a little checklist. Each of the rivers in the state are classified by their size, and the electrofishing station length is on average about 30 sometimes the stream width. I think it might be 35. I can't remember the exact number off the top of my head. And then as the size category gets larger, so we have two small categories, but then medium, large, very large, the electrofishing station length gets correspondingly longer because the average width gets longer. And with that, the spacing of the transects for measuring habitat increases. And so we're going to be looking at a stream. In this instance, it would be a small stream, more than 15 feet wide, so we'd have an 800-foot electrofishing station, transect spaced 60 feet apart. And then it results in you getting about 13 transects where we collect data. And then we sample at different spacing along the transects, 1/5, 2/5, 3/5, 4/5 of the way across the transect and the thalweg. So you measure the width of the stream, and then you take about 1/5 of that, 2/5, and then collect the measurements on the transects. This data sheet also is important. It has definitions for riffles, runs, pools, which might seem obvious to most of us, but so we're measuring things the same way. Other attributes like artificial log jams are described, brush deposits, a log jam is defined, and these things are defined so we have a specific and even footing in terms of how we are classifying different types of habitat. So we're going to get on to the first transect and collect some measurements at that transect. We're going to the transect data sheet.
Whenever we do a survey, it's important to include as much information as possible. For example, on the top of this sheet, we have the water body, so that would be the river being surveyed. The station, that would be a description of where you're electrofishing. An example of that could be Cherry Creek from the county road, 480 crossing downstream 800 feet. You can also include details about the beginning or end of the station, such as station begins at a 12-inch DBH cedar tree on the left bank. The date, Valley Segment ID, you don't have to worry about that. We can find that out later. The crew, we typically put the first initial, last name. Most important thing is to put which agency or organization you're with. Any comments you have on the survey, and GPS coordinates are really important because with those, someone can go back and find the exact start and end of your station.
Number the transects from downstream to upstream. Typically, we would we'll measure the station out, so we'll go, for a transect spacing of 60 feet, we'll measure 60 feet, then 120, and then number the transects. And you number from typically downstream to upstream, with transect number 1 being the furthest downstream. And then we would follow back up and just, we would mark them with flagging tape. Just take off the flagging tape as we go back, and then you're all done. So the first thing we're going to do is get the width. And we have two types of width. One is the wetted width, which is the width of the part of the channel that's carrying water, and the other is the total width. And that includes, it might include islands that are in the channel itself. And in this example, this isn't exactly an island, but imagine that there's water flowing all around that on both sides. And you'll see that when we measure that, you measure the amount of the width of the area where there's water, and then you measure the width of the island, and then you measure the part of the channel again carrying water, and then those added together equal the total width. And so you'll see how we do that in a minute. So I'm going to give Dan our total width So total width is 31.4. So you divide that by 5 and you get about 6.3 feet per, that's our spacing. So the first measurement will be at 6.3 feet. There'll be a few pages of these data sheets that we're going to flip through as we go along, taking data on the transect. So the first will be the width of the transect and then information from that transect. And then at the banks, there are some measurements that are taken right at the bank. So first thing you do is we note the riparian. So this is the riparian and bank condition data sheet. And we characterize what the riparian conditions are. Noting the dominant vegetation, it's something that's more than 50% or so, within 30 feet from the water's edge and 30 feet upstream and downstream of the transect. So you just kind of look upstream and downstream, and you can see that it is fairly subjective. Often things are mixed up, but I think this might be reasonable to say this is predominantly tag alder types. But we're doing this at every transect, so 13 transects, 2 banks. So when you add all that information up from all those measurements, it'll turn into a fairly quantitative kind of measurement. And in the past, people would not, they might just say wooded riparian, or they may not say anything. So we're trying to get some kind of quantitative information, but we're not trying to make it overly burdensome to characterize the channel on site. So the first thing we're going to go is the bank. So we'll say we're at transect number 1 here. The riparian class is tag alder, so you put a TA there for tag alders. The bank stability, let's see, here's the stability classes. So when you're assessing the vegetative stability, you assume the channel is full of water, which kind of it is in the spring here, and you look at the river where the river would be touching the stream bank, and look at how much of the bank is bare soil. So in this upstream downstream area, and you can see most of this it's vegetated with grass. There is some bare soil there, but this would be a very less than 25% is bare soil, so we'd say the stability is good. So you just give that a score of 1. And then we take these couple measurements. One is the undercut length, and then also the stream shore depth. So if there's an overhanging bank, you take your measuring stick and you measure back from that bank as far in as you can reach and see what the length of that undercut is. Trout do like undercuts, and I'm sure other fish use them as well. And then also the stream shore depth, which is right at the edge where the water meets the shore. We measure the depth there, because sometimes it can be fairly deep at the stream shore, which this shows. So Dan's going to start getting our data. So you want to do the undercut length?
Sure. I guess we can just simulate one if there was an undercut. So if like this log was actually the bank, for the undercut you would just measure underneath it as far as you can go to give the measurement for how deep the undercut is. So there would be like 0.8 feet. And then also you would do the stream shore depth at the undercut, which would be at the edge of it straight down to see how deep the water is. At this actual transect, there is no undercut. So what generally happens is you'll have 0, 0. You'd have no undercut and a stream shore depth of 0 because the water just comes up to the edge of the bank. So there's technically no depth at the stream shore. So for this one, it would be 0 undercut, 0 stream shore depth.
All right.
And at our...
That's 6.3 feet.
6.3 feet.
So we flip back to this data sheet. What did we say that width was? 31.6, I think. 31.6, okay. Oh, that was it. Okay, so at the first, this is 1/5 the way across. He's going to give me a depth.
The depth will be 0.2 feet.
0.2 substrate.
The substrate will be primarily detritus.
And we've got codes here showing that right here, so use those codes. Everyone in the state's doing this the same way, so we want all of our data to be comparable. If there are gravels, we note if the gravels appear to be more than 50% or less than 50% embedded, which means buried by finer substrates. Here we don't have any gravel, so you just record 9 for gravel. Do you have any percent wood?
0% wood, and I'd say 70% vegetation.
And then, so when we're looking at dominant substrate, it's within a 1 foot diameter circle at the sampling point. So he's noting the dominant substrate, what percent of that 1 foot diameter circle is wood, and what percent is rooted plants. And rooted plants are often ignored in many stream surveys, but they're important habitat for a lot of fishes. Okay, so now we got this, we're coming up to the island, so you can give me the width of the channel up to the island.
So the edge of the island is at 6.7 feet. The far end of the island is at 9.7 feet. When measuring the total width and wedded width of a transect, it's important to calculate those measurements correctly. The total width is from where the water meets the left bank to where the water meets the right bank, and the wedded width is the total width minus the combined widths of any islands. So for this example, the first part of the channel was 0 to 6.7 feet. The island was 6.7 to 9.7 feet, meaning the island was 3 feet wide. You can calculate that number out in this box or just include the measurements. I like to include both. Then the remaining channel was 21.9 feet wide. So the wedded width is the 6.7 feet plus the 21.9, giving us a wedded width of 28.6 feet.
And the next measurement is going to be at 12.6. It's going to be our 2/10 of the way across the channel. So he's going to do the same thing, basically get a depth.
12.6, it is 0.9 feet
0.9 substrate.
Substrate is primarily sand.
Sand is an S.
There is no plants.
Embeddedness is unmeasured or not relevant. Shouldn't say not relevant, but it's unmeasurable or not applicable. No plants.
And approximately 40% wood.
40% wood. Okay, so all of these blanks should be filled in as you're going across. And
then the 9s is not applicable.
Right. Yeah, because there's no gravel there.
Or unmeasurable.
Or unmeasurable. Yeah.
So if the water's too deep or turbid to see, but you can tell if it's what the bottom is, you still put unmeasurable because you can't actually see the embeddedness.
The next one is at 18.9, unless you get to the thaw leg, which you might be doing here in a minute. And so one of the areas that we take a measurement in the thaw leg of the channel, and for this program we define the thaw leg of the channel as the deepest part of the channel. And usually that's often the part that carries the bulk of the river's current. Technically the thaw leg carries most of the river's current, but it's kind of difficult for different people to judge that. So we just go with the deepest part of the channel because those two are often the same. Dan is comparing areas to see what he thinks would be the thaw leg.
The deepest with the most flow seems to be about at 1.6 feet deep.
So in thaw leg we write that down, 1.6.
Predominantly sand.
Sand, and it's good to have people taking the data that have legible handwriting. Mine isn't always the greatest, but we do have to read this and enter it, or someone does. It will get entered.
And I'll do about 10% plants,
10% wood. 10% plants, no wood, and the embeddedness is unmeasurable. Okay. The next one is going to be at 18.9.
Depth is 1.0.
Okay.
And there's some rocks, but still, I think, primarily sand. No plants and no wood.
No plants, no wood. All right. The next one will be at 25.2.
So when there's a log or some other obstruction on the transect, if it's a large boulder, I'll do it right on the boulder because that is basically the substrate. But when it's a log, I'll just go as close as I can to my actual point and go right down to the bottom. So here the actual depth isn't 0.2 feet, it's below the log. So it's about 1.7 feet deep here. is primarily sand.
So embeddedness is not applicable.
There are no plants, but the majority of this spot is actually wood because of the logs, so I'd say it's about 90% wood.
And again, you don't want to get into big arguments over it's 90% wood or 80% wood, because in the end of the day, we'll have looked at 13 transects, and each will have 5 points at each transect, so we're going to have about 80 some points, and those slight differences will average out when you start to assemble all the data together and take an average for the channel. Okay, here we are at the other bank. So that's the left bank we did. Now we're going to go to the right bank in transect number 1. And so looking at our dominant vegetation in the riparian area, again, it's by and large tag elders, I would say. So we'll put that down. Tag elders, bank stability, look 30 feet up and down. The whole area looks vegetated, so that stability looks good. Undercut length, what you got?
There's no undercut, but there is some depth here at 0.1 feet.
0.1 feet, so. And if there's no undercut, write down 0, so there's no question what the situation is, and 0.1 feet. For each transect, record the predominant habitat type, and so the options are riffle, pool, and run. And those are defined on this handy dandy page here. Here are the definitions. For riffles, have shallower than average maximum depths and obvious surface turbulence. Water velocities faster than average. Runs have average maximum depths and little to no surface turbulence. Water velocities may be fast or slow, but water surface is generally smooth. Pools have deeper than average depths and no obvious surface turbulence or broken water. Water velocities are always slow. So this is a little bit tricky, that we do have surface turbulence, but it's predominantly sandy.
Is it also created by this log? The
Yeah,
turbulence?
the surface turbulence is due to these logs. It's not due to a riffle or anything. My inclination would probably be to call this a run. There's not a lot of. It's a pretty uniform channel morphology, aside from what the wood provided here. But you know, this is kind of subjective, but I'd probably call it a run. And again, we make these observations on 13 transects, so it'll start to average out a little bit. What do you guys think? Would you call that a run, or?
Generally, when we're looking at riffles, the riffles caused by gravel, cobble, that sort of thing.
Yeah.
Just some woody debris in the stream is causing most of the surface disruption here, so I would call it a run.
Wood is a key aspect of habitat in many river systems, and in a river like this, where it's by and large sandy, the river would have a fairly uniform channel depth and velocity profile within the channel. If it wasn't for wood, you can see wood kind of breaks up the flow of the river, forces it around the wood, which gives you a little extra depth. It causes some sand to be brushed aside and exposes gravel, and it adds areas of low velocity and higher velocity to the channel. So and then it provides just visual cover for fish and other animals, and substrate for supporting invertebrates and stuff. So it's really an important part of habitat. And what we do on our surveys is through the entire length of the reach where we're sampling. So if it's an 800-foot electrofishing reach, or in this case, an 800-foot habitat survey, we quantify the amount of wood in the channel. And so what we do, we count individual logs that are at least 6 feet long, 6 inches in diameter, and the portion of the log that's in water that's at least 6 inches deep. And so we simply, the data sheet notes what size class the wood is. It can be a log that's more than 6 inches but less than 12 inches. We note these bigger logs because they provide kind of unique habitat due to their size. So we have 4 size classes. This is diameter at breast height. So it would be the typical lower portion of the tree. And then this is the number of full 6-foot sticks lengths. And what Dan has is a stick, and we'll provide one of these to you, or you might need to make one. That's incremented. It's the total length of that stick is 6 feet. So the log should be 6 feet and it has 6-inch increments on it. So you can just hold that stick up to your log and see if the log that you're interested in is over 6 inches deep, 6 inches wide. And then you can stick the end of that in the water to make sure it's in water at least 6 inches deep. And so we record the number of stick lengths. So it gives you an idea if it's a short log, you know, something that's 6 feet long. If it's, and this is the number of full stick lengths. So this one here that you would, if we count one of those, you just put a tick mark in there, and that would be a log that is at least 6 inches diameter and it's at least 12 feet long, the portion that's in the water. And so we just go up the river counting those logs. We also note log jams, beaver dams, and brush deposits. Those are defined on this one page earlier on that has all the definitions. And we just use that stick there. We categorize it by what it is: log jam, beaver dam, brush deposit. Put the category there, put the length and the width, and you just measure it, ballpark it with that stick. And it gets to be, it can be tricky to do, but think of it at the coarser scale. It allows you to distinguish rivers that don't have much wood from others that have a lot of wood, to some that have maybe average amounts. And it allows us to put numbers on these things, you know, kind of ballpark numbers, and then compare one river to another. And so we can talk about the density of individual logs or woody structures in one river versus the other. So we usually start at one end of the river, one end of the study reach, and go to the other end. So Dan's just gonna come up through this reach. You know, this was where our first transect started. So he's just going to come up through here and show you how we do it, and I'll show you how we record the information. We also distinguish natural structures from artificial structures. And, you know, artificial ones are ones where you can see that it was obviously made by humans for one reason or another. Just so we can distinguish that.
So this log's about 6 inches diameter, so it'd be 1, 2, approximately 3 6-foot lengths long, so it is a 6'3". This one's roughly 6 inches. This one's about a 6'2".
And I'll note that in the past on surveys, they usually often didn't take any notes or counts of wood. It was usually not noticed or not mentioned, or they'd say a little bit or lots, but there's little information collected, so we're trying to provide some quantitative information that's standard across surveys.
So this log is closer to 12 inches across. So this one in the river I do approximately there, or there, it's about 3, so it's a 12'3". There's more over here. This one's closer to 6 inches. It's about 6 feet long, so that's a 6'1". And then this one, usually we measure from where it comes out of the river. It's a little smaller than 6 inches there, but up here it's 6 inches at least. So approximately, so it's 2.5. It's a little less than 2.5, so we call it 6'2". It's a lot of rounding basically to the nearest measurements.
Number of full stick lengths. See over here, this would be an example of something we might call a brush deposit. None of it's over 6 inches in diameter, but it's a bunch of pieces of wood together, and collectively they're making habitat for fish. So we would use that woody debris stick and just kind of roughly measure the amount of that is kind of as a unit of a deposit.
So the length and width of it.
Maybe Dan will demonstrate.
Yeah, this stuff's obviously very subjective also, but for this one, it's sort of this area. It's about 30 inches by, that'd be approximately 6 inches there. The edge, about 8 feet by, well, roughly, we'll say about 8 feet by 3 feet.
Mm-hmm. And we just record measure the area that's obviously in water deep enough, so it has to be at least in 6 inches of water, because sometimes these things will run up into the banks and we don't keep that. And then on the data sheet, you just record, you know, BRD, fresh deposit, the length and the width. And then when that data is entered, we calculated an area for each of these deposits. We add them all up, and you get a total area of woody structure, that's natural, total area of artificial structure, amounts of individual logs by size class. We're trying to be standardized in our approach, but there are situations that are very difficult or can be difficult to judge. The definition of a log jam is 3 or more logs that are intermingled together. And you can see these logs are laying on top of each other, but you know, some of them are barely in the water. Really, this one here is in the water, and it's certainly of a size that you'll count. This one here, this one is mostly out of the water except for that very end, and over at that end it's really too small to be counted. This one here is basically entirely out of the water, so I would probably just measure this one individual here as a single log, and these other two probably not include them. But other log jams are very obvious, you know, the big piles of logs and debris all in there, and just measure the length and width as best you can. I mean, we understand that the shapes of these structures can be very amorphous and hard to represent with 2 measurements, but we just try and give it our best, give it an average length and width, and then move on. Well, some of you might be thinking, you know, why do we have to measure discharge? It kind of looks like a time-consuming process, but typically, you know, maybe we could get it from a gauge. Well, usually there's not a gauge on almost any river you're going to be working on, and this is the only time you're going to get information on what the flow actually was on the day when you were there. So it's a fairly important thing to record. It does take a little bit of time, but it's the only way to capture that information on the day when the survey occurred, and that will help users to understand if the depths seem deep. It might be because the flow is high that day or low another day. So it's useful to have that information as a reference. As the rivers get bigger, the spacing of the velocity measurements increases, and so we have 3 different data sheets. One's for less than 30 feet wide, one is for streams 30 to 60 feet wide, and for those, you're taking a measurement every 2 feet. We also have a measurement for streams that are 60 to 90 feet, and those you take a measurement every 3 feet. So everything kind of scales out as the rivers get bigger. But most of the surveys, they're commonly these smaller streams. As we mentioned, that wood in the other part of that reach up there made the channel flow pretty dynamic in terms of velocities, variability in velocity. And when you're estimating stream discharge, which is something we do on all of our habitat surveys, you ideally want the channel to have a straight, uniform velocity and depth characteristics if possible, but velocity. So it's not, you don't have a lot of turbulence and eddies and pocket water. And so we drop down a little ways from our site, but you want to be within your reach or very close to your reach. So it's, you know, the same discharge as what you were working in. And we found this portion of the river, this is just around a bend, and you can see there's a nice, fairly straight channel, depth fairly uniform, velocity is fairly laminar, straight, not turbulent. And so we set our transect up here. You want your transect line, as when you're doing habitat transects, you want the transect line so it's perpendicular to the flow, so you can see the flow is coming straight down, and our transect line's at a 90-degree angle. And then we take our discharge measurement data at equally spaced points on that transect. And so for a stream that's less than 30 feet wide, we sample at 1 foot intervals. We record the depth and take the velocity at 6/10 of the depth. So for example, if the depth is 1 foot, you measure the velocity at 0.6 feet below the surface of the water. And so when you're doing the discharge, like at the other spots, note the water body, the station, the date, the crew, the description of the discharge measurement transect, because it might be different than, well, it will be different than all the other habitat series probably. The latitude and longitude for it, Oftentimes, if you're a little ways above or below a bridge, the channel could be fairly uniform there, and those might be good locations. Or if it's just a straight run, that would be good. So now we're going to take some discharge measurements. The special piece of equipment you would need is a current meter, and Dan's got a Marsh McBurney current meter. There's different models, and so we'll have him take some measurements. So you need to know how to use your equipment. But
and you can record these in meters per second or feet per second. It's just really important to know on the data sheet which units you are using.
Yes, and that ours is the case in point because our depth measurement device there is in centimeters, and then
and then we're measuring in meters per second. So
yeah.
We're doing it in metric. I mean, the data sheet is set up, I think, for standard.
Yeah.
But either way, it's fine as long as you know which units you're using.
So just cross out the English and write metric if that's what you're doing. Okay. So
first measurement at the stream shore, there is a depth of approximately 2 centimeters. And a flow of 0.
okay. And what's your flow units?
Meters per second.
Meters per second. So just cross it out, do this. Okay, and the next one is at 1 foot?
At 1 foot, depth would be 8 centimeters. It's important to stand back so that your feet aren't influencing the current.
Mm-hmm. And you want the head of the device that's taking the measurement to be pointing directly into the current, so not on an angle, but just pointing straight into the current.
It's 0.01.
But if there's an eddy or a backflow, you don't turn it so it's pointing backwards or anything.
Yeah, these
Right.
will read negatives.
Mm-hmm.
We always enter the negatives as zeros, so it doesn't really matter on the data sheet if you put negative or 0 because we always enter them as zeros. So at 2 feet, the depth is 22.
So we just do this going across.
So this is an example of how we actually take measurements at a point on our transect. We use the flow meter. This one's a Marsh McBurney flow mate, and it's top setting weighting rod. The first thing we do is measure the depth at the point. We measure the depth using the rod, the front part of it. It's marked every 2 centimeters with a single mark, every 10 centimeters with a double mark, and every 50 centimeters with a triple mark. I usually start at the top and go down, so for this one it'd be 50, 40, 30, about 28 centimeters deep. And to get the sensor at the appropriate depth, so this one was 28, so I move this number, so 2 for 20, up to the 8, meaning the depth is 28, and now put the sensor 1/3 off the bottom of the water height. So we just make sure that the sensor is facing upstream and that we're standing back from it so that our legs aren't inhibiting the flow. And then we watch the screen, which gives us measurements. It actually does, it's averaging. So there's says period, and usually I just let it cycle through a couple times until the numbers tend to stabilize. So right now it's at 0.26, it's 0.25. I'll probably let it go one more time. And if the numbers are really close, I'll go with the measurement. If they're jumping around a lot, I'll let it go a few more times. So I jumped just a little bit. I'll go one more time. So we had a 0.25, 26, 27. And it's stabilized, so 0.27 meters per second.